I'm going to discuss one of the most celebrated differential equations in all of mathematics, and that's the Legendre ordinary differential equations. The solutions to the Legendre equation are the famous Legendre polynomials. The way this works is this differential equation, you can see that it's got polynomial coefficients. So that's one of the reasons why polynomial solutions are expected from this, although it's not immediately obvious. For example, because you have 1 minus x squared multiplying the y double prime term and x multiplying the y prime term and a constant multiplying the y term, you can expect that if y, for example, is a second order polynomial, then this would be a quadratic term, and that'll still be a quadratic term, and that'll still be a quadratic term. So there's some chance of this being equal to 0. So that's one of the intuitions you can expect to start with. The solutions can be found by the usual methods of series solutions. So we'll expand it in terms of a series, an x to the power n going from 1 to infinity, so that y prime will be the sum n equals 1 to infinity, because the first term a naught will become equal to 0 when you take the derivative, and so you only have terms starting from a1. So that's n a n x to the n minus 1. And y double prime, by the same reasoning, the count starts from n equals 2 to infinity, n times n minus 1, a n x to the n minus 2. Now, the only subtlety here is that even though x to the n minus 2 times x squared is x to the n, 1 when multiplied by that is not x to the n, it's x to the n minus 2. So we have to take care of that. So let's substitute everything in to the Legendre ODE, and I get 1 minus x squared sum, I'll omit the summation range, a n x to the n minus 2 minus 2x, the sum n a n x to the n minus 1 plus l times l plus 1, sum a n x to the n equal to 0. The way something like this is further advanced is to compare the coefficients of both sides. So x to the n coefficient must be set equal to 0. So because the right hand side does not have any x to the power n. X to the power n occurs in the first term where 1 multiplies when you advance the index by 2. So that I'm going to get n plus 2 times n plus 1 a n plus 2, because that gets multiplied by x to the n when you advance the index by 2, since 1 does not contribute a power of x. For the next one, you keep x to the n minus 2, because x squared times x to the n minus 2 gives you x to the n. So you don't advance the indices any. So I get n times n minus 1. Not advancing the index means just copy it down as is, a to the n. So that's all the first term. The second term, I don't advance again, because x times x to the n minus 1 is x to the n. So I just copy down the index as is. So I get 2n a n. And the last term, exactly the same way. X to the n is the bare coefficient here, so I get plus l times l plus 1 a n equal to 0. So that gives us all the recursion we want, because a n plus 2 comes in terms of previous coefficients, namely a n. So we can do this as follows. I'll leave some of the algebra to the notes. So I'm going to get a n plus 2, and you can write this in this peculiar fashion. A n plus 2 equals n times n plus 1 minus l times l plus 1. That's the reason, by the way, for choosing the coefficient here to look like l times l plus 1, because you get this n times n plus 1 behavior on the numerator, divided by n plus 1 times n plus 2. So by the way, this immediately shows us that a n plus 2 is 0 when n is equal to l, which means that there's an absolute stop to the this is times an, to the advancement of this series. So that means the solutions are all going to be polynomials. Now, you can also show the solution above converges. Since an plus 2 equal to 0 for n equals L. Alright, so these solutions are polynomials, and for different values of L you can determine the nature of the polynomial. Now, it turns out that you get two kinds of series. For L equals even, you get one kind of series. For L equals odd, you get another kind of series. And alternately, the even and the odd alternately converge or diverge. So I want to just show you how it works for L equals 0 and L equals 1. For L equals 0, it just means put L equals 0 in that formula. So I get an plus 2 is equal to n times n plus 1 divided by n plus 2 times n plus 1. So you notice that n plus 1 cancels out and times an, and I get n over n plus 2 times an. So I can, let's say, try the odd series first. If I try the odd series, a1 is the term that's not equal to 0. So I'm going to get a3 equals 1/3 a1. So n equals 1, that is. And then I'm going to get a5 equals 3/5 a3, which is equal to 1/3. So it ends up being 1/5 a1. So you're going to end up getting a2m plus 1 is equal to 1 over 2m plus 1 a1, basically. So the solution y for the odd polynomials, for the odd values of assuming that a1 is not 0, ends up being a1 times 1 plus 1/3 plus 1/5 plus 1/7 and so on. Now this is a harmonic series and it diverges. It goes to infinity. So it's a divergent series, and so the odd solution does not exist. The even solution is the only one that is there. For L equals 1, you will find the opposite. You'll find the even solution is the one that goes harmonic. So let's try this. Let me try to prove that. So n plus 2. Now it can be shown that this for L equals 1, I can write this as follows. I can write this as negative 1 minus n times n plus 2 divided by n plus 2 times n plus 1. Okay, so n plus 2 term cancels out times an, and that gives me negative 1 minus n over n plus 1 times an. Now if you, just like here, take a naught to be not 0, then I'm going to get a2 equals negative 1 because of negative sign. For this, for n equals 0, negative 1 a naught, and then I get a4. When I put 4 means 2, n equals 2, so I'm going to get 1 minus 2. That gets rid of the negative sign, but on the denominator I'm going to get 1/3. So that's going to be negative 1/3 a2, but a2 itself is negative 1 a naught, so that gives me actually this is positive 1/3, so that gives me negative 1/3 a naught. And so you can show that a to the if you keep generalizing like this, a to the 2n is equal to negative 1 to the power n, 1 over 2n plus 1 a naught. Let's see if this works. N equals 0. It does not work, so I'll put negative 1 over here just to make sure it works. Okay, now it'll work. That's a general term. So the even series, y even for L equals 1, that's for L equals 0, that's for L equals 1, ends up being negative a naught times 1. Oh, by the way, I should have put x and x squared and all that here. So this is y x squared, x cubed, x5, x7, and so on there. And this goes to plus or goes to infinity at x equals 1 is what I should have said. So the even function here, I get 1 for the a naught term. A naught does not multiply x, so I just leave it there. For the a2 term, I'm going to get minus, so that's a minus. That is a naught, and then the a2 term is minus x squared, and then the a3 term is plus. And that also diverges at x equals 1 or minus 1. When I say 1, I mean 1 or minus 1. So you are going to end up getting divergent series. So the alternating, the main point of this discussion is to show that you don't get two solutions. You only get one solution from this procedure. A second order differential equation has two solutions, but for every value of L, you only get one solution. For L that is even, the odd series diverges. For L that is odd, the even series diverges. So only the only solution you get is a solution that is polynomial of order L. So that's the bottom line of this discussion. And that's a serious problem. How do you get a second solution? In a later video, I'll show you the second solution can be got using the Bernoulli technique we learned in previous videos. So only one solution converges at the endpoints for each value of L. These solutions, as I said, are called Legendre polynomials, and the Legendre polynomials can be given in terms of an actual formula. I'll write it down here. Don't be too scared. I will, in later video, show you how better formulas can be got. But if you do a computation of the nth term and you write everything out, then it turns out that PLX can be written as the following. It's a sum where k equals 0 to n, because remember it stops at n, negative 1 to the power k. This is 2l minus k factorial, x to the l minus 2k divided by 2 to the power l k factorial, l minus k factorial, l minus 2k factorial. So for L equals even, you have your summation go up to L over 2. And that's possible because L equals even means L is something like 2 times an integer, so you can divide by 2. If L equals odd, then your upper limit of the summation in the number of terms is L minus 1 over 2. So this is the prescription, and you can put this in a computer and it'll generate all the polynomials for you. So this is certainly one way to go. But even doing this by hand for very simple cases is a chore. And so it's not a recommended strategy to use this in daily life. There are much better ways of finding out the Legendre polynomials, especially for low values of L. And we'll be looking at those in the future videos.